2024 February 17, Saturday. Complex Piping Design Guide for Self-Regulating Heating Cable. Table of Contents, Introduction, Computer-Aided Design Program, Heat Tracing Design Outline, Basis for a Good Design. Step 1. Establish design parameters. Step 2. Determine heat losses. Step 3. Select the proper Sermon heating cable. Step 4. Determine heat tracing circuit lengths. Step 5. Choose options, accessories. Design tips, design worksheets, general specification. This design guide displays information in English and metric values wherever possible. Certain tables have been displayed in English values only due to space constraints. Contact Sermon to obtain these tables in metric values. Introduction. This design guide addresses the heat tracing requirements of complex piping. Whether the application is a small project or a complete network of piping and equipment, designing an electric heat tracing system for complex piping is simplified by using Sermon self-regulating cables. The information contained in this design guide will take the reader through a step-by-step procedure to make proper heating cable selections based on pipe size, thermal insulation type, and thickness, desired maintenance temperature, maximum exposure temperature, minimum ambient temperature, heating cable startup temperature, available power supply, electrical area classification. After following the prescribed steps in this design guide, the reader will be able to design, select, and/or specify or establish a bill of materials for a heat tracing system. Typically, complex piping is located inside the process unit and consists of a relatively short branch of pipe with frequent teeth, as well as inline valves, pumps, and related process equipment that also requires heat tracing. Circuit lengths can range from several feet less than 1 meter to several hundred meters in length. However, the average is usually 100 feet, 30 meters or less. For applications ranging from protecting water lines to maintaining elevated process temperatures as high as 302 Fahrenheit, 150 Celsius, Sermon self-regulating cut length parallel resistance heating cables are recommended. Variations in the heat loss of the insulated pipe due to equipment, supports, and/or insulation are compensated for by the heating cable's PTC, positive temperature coefficient characteristic. Sermon offers heating cables specifically designed, manufactured, and approved to cover a wide range of applications. PSXX, designed for freeze protection and temperature maintenance at or below 100 Fahrenheit, 65 Celsius. PXX is well suited for both metallic and non-metallic piping and equipment. 1. Nickel-plated copper bus wires. 2. Radiation cross-linked semiconductive heating matrix. 3. Polyolefin dielectric insulation. 4. Tinned copper braid. 5. Polyolefin or fluoropolymer over jacket. RXX52, designed for applications where the watt density requirements preclude the use of the standard range of PSX cables. 1. Nickel-plated copper bus wires. 2. Radiation cross-linked semiconductive heating matrix. 3. Polyolefin dielectric insulation. 4. Tinned copper braid. 5. Polyolefin or fluoropolymer over jacket. HTSX, designed for process temperature maintenance or freeze protection applications up to 302 Fahrenheit, 150 Celsius, and intermittent exposure temperatures, power on or off of 482 Fahrenheit, 250 Celsius, and continuous exposure, power up to 400 Fahrenheit, 204 Celsius. The cable is capable of withstanding the exposure temperatures associated with steam purging. 1. Nickel-plated copper bus wires. 2. Semiconductive heating matrix and fluoropolymer dielectric insulation. 3. Nickel-plated copper braid. 4. Fluoropolymer over jacket. VSX HD, designed for process temperature maintenance or freeze protection applications up to 392 Fahrenheit, 200 Celsius, and intermittent exposure temperatures up to 482 Fahrenheit, 250 Celsius. 1. Nickel-plated copper bus wires. 2. Semiconductive heating matrix and fluoropolymer dielectric insulation. 3. Nickel-plated copper braid. 4. High-temperature fluoropolymer over jacket. USX designed for process temperature maintenance and freeze protection applications up to 464 Fahrenheit, 240 Celsius, withstands intermittent exposure temperatures, power on or off, of 482 Fahrenheit, 250 Celsius, and continuous exposure temperatures, power off, to 464 Fahrenheit, 240 Celsius. Number 1. Nickel-plated copper bus wires. 2. Semiconductive heating matrix and fluoropolymer dielectric insulation. 3. Nickel-plated copper braid. 4. Fluoropolymer over jacket. Computer-aided design program. Surman has developed a sophisticated yet easy-to-use computer program, CompuTrace, that provides detailed design and performance information. Users of CompuTrace are able to input application-specific information into the program and obtain detailed electrical and thermal performance information. Calculations made within the program are based on the formulas prescribed in IEEE Standard 515. The information input to and/or generated from CompuTrace can be printed and summary report, including load chart information, exported for use in other programs. While CompuTrace is a valuable asset to use in designing a heat tracing system, the design steps detailed in this guide will still form the basis for identifying the design process necessary to establish a properly functioning heat tracing system. Heat tracing design outline. The 5 steps below outline the design and selection process for an electric heat tracing system. The step-by-step procedures that follow the outline will provide the reader with the detailed information required to design, select, and/or specify a fully functional electrical heat tracing system. Step 1. Establish design parameters. Collect relevant project data. A. Piping equipment. Diameter, length, material. Temperature, low ambient, startup temperature, maintain temperature. High temperature, limit excursions. Insulation, type, thickness, same size, oversized. Electrical operating voltage, circuit breaker capacity, electrical area classification. Step 2. Determine heat losses. Using information gathered in Step 1 and based on heat loss chart tables, computer design programs, CompuTrace. Select the proper thermal heating cable based on application requirements, maintain temperature, maximum exposure temperature, watt density requirements, power output at maintained temperature, electrical design, available voltage, circuit breaker capacity, cold start impact, approval requirements, hazardous area approval, code requirements, determine heat tracing circuit lengths based on cable selection, electrical design, and pipe lengths with allowances for valves, pumps, supports, other equipment, circuit fabrication and splice kits. Choose options accessories. Minimum installation accessories include a power connection and end termination kit. B. Cable attachment tape. Optional accessories include thermostatic control and monitoring. Basis for a good design. To become familiar with the requirements of a properly designed electric heat tracing system, use the 5 design steps detailed here and on the following pages. Once comfortable with the steps and the information required, use the design worksheet included at the end of this design guide for applying these steps to a complex piping application. Step 1. Establish design parameters. Collect information relative to the following design parameters: application information, pipe sizes or tubing diameters, pipe lengths, pipe material, metallic or non-metallic, type and number of valves, pumps, and other equipment, type and number of pipe supports, expected minimum ambient temperature. Generally, this number is obtained from weather data compiled for an area and is based on recorded historical data. There are times, however, when the minimum ambient will not be the outside air temperature. Examples include pipes and equipment located underground or inside buildings. Minimum startup temperature. This temperature differs from the minimum expected ambient in that the heating cable will typically be energized at the higher ambient temperature. This temperature will have an impact on the maximum circuit length and circuit breaker sizing for a given application. See circuit length tables on pages 8-12. Insulation material and thickness. The selection charts in this design guide are based on fiberglass insulation with thickness shown in tables 2.2 through 2.7. If insulation materials other than fiberglass are used, refer to the insulation correction factors shown in table 2.1 or contact Sermon or a Sermon factory representative for design assistant. Supply voltage. Sermon self-regulating cables are designed in two voltage groups, 110-130 VAC and 208-277 VAC. Determine what voltages are available at the facility for use with heat tracing. All information in this design guide is based on metallic piping. For non-metallic applications, contact Sermon.